This is lecture video 38, and in this video we start chapter 6 titled Applications of Definite Integrals. As we remember, we covered in the previous chapter how to use definite integrals to find the areas under the curve or areas between two curves. And in this chapter, we extend the application of the definite integrals to finding volumes. We will be computing volumes by using definite integral in this chapter. And in the first section, we define volumes of solids using the areas of their cross sections. Like here, a cross section of a solid is the plane region formed by intersecting our solid object S with a plane like this. So we call this plane Px as it is the plane over the x point on x coordinate. Okay, so if you consider the cross-sectional area of this shaded part, let's call it as A of x. Okay, this is what? This is the area of the cross-section Then you can use this cross-sectional area to compute the volume of the whole solid object S. How can we do that? So at each point, over each point on x-axis, you will be having such cross sections, right? Over here, over also here. For each point on x-axis, over the interval a to b, you have such cross sections. And if you sum up the areas of these cross sections, you expect to obtain the volume of the whole solid object, right? So, and we want to sum all those cross-sectional areas continuously from A to B, and integral does this job for us. Integral is a continuous summation. So if you integrate the cross-sectional areas A of x from A to B, which is this interval, you will obtain the volume of your solid. Okay, so this is the general idea. Now I will try to explain it in more details. Okay, now this is our solid object S again, and you are taking this slab in the solid object S. Slab means very thin cross-sectional area, but it has now this thickness. Now, if you zoom into this slab, zoom into this part, you see such a figure, and as you notice, there are some error terms here because slab means this cylindrical kind of object, but that it is bigger than our usual solid. And here, this part is the cross-sectional area, A of x, that we have mentioned above, cross-section. And we are interested in this interval between the points xk minus 1 and xk, and it is here in this picture. Since we are zoomed in, it looks bigger, and we will be calling this as delta x. And now please consider the volume of this cylindrical slab. Okay, so how can you compute the volume of this cylindrical object? Let's call this volume as bk. Of course, it will be base times its height. So how do you find the volume of cylinders? Base times the height. And what is the base of this cylindrical shape object? It is A of x. Base is given by the cross-section area, and height is given by this length. So, and I called it as delta xk, okay? So height is given by delta xk. So this expression gives us the volume of the Kate slab. And instead of delta xk, you can write this difference, xk minus 1. So the volume of the Kate slab is given like that, as it is written here. Okay, the same thing. Now, we want to In fact, this is the volume of the cylindrical object here, but the Kate slab is the smaller, the actual solid inside it. That's why volume of the Kate slab is approximately the same as the volume of the Kate cylindrical shape here. That's why we have this approximate sign. As you can see, there are some error terms here. Okay, then what we want to do, we want to relate the volume of the whole solid to this Kate slab. Then you can do the same thing over each sub-interval, that you divide your interval AB into Kate sub-intervals. Over each Kate interval, you will be seeing this. That's why now we want to sum them up, like here. Okay, what we are doing here is we are summing up the volumes of all volumes of all cylindrical shapes. The Kate one is seen here, so Vk from 1 to n. So the formula becomes like this then, and I want to warn you again about this approximate sign. Why we need to put this approximate sign? This is the volume of the solid. Volume of our solid S, and it is approximately the same as the volume of the sum of all cylindrical shapes like this that you obtain over each sub-interval. So they are not the same because of these error terms. And Vk is computed like this, as we discussed here. And if you put the limit as n goes to infinity, what will happen? If you divide your interval into n sub-intervals, then you sum from 1 to n. And if you want to get rid of these error parts, you need to divide into more sub-intervals. The more sub-intervals means the less error you have. And finally, you understand that if you put limit n goes to infinity here, when n being the number of cylindrical parts, you will obtain exactly the volume you want, okay? You see, instead of approximation sign now I turned it to the exact equal sign when I put the limit as n goes to infinity. And this kind of sums are called Riemann sums that we have covered before, and it is the same as this definite integral, okay? So the volume of your whole solid object is in fact the definite integral of the cross sections AX from A to B, okay? So in fact, we covered this idea here, but here are more technical details why the volume is given by this definite integral. Okay, this is the formal statement about what we have covered about the volume. So volume can be found by taking the definite integral of the cross sections over the given interval AB. Okay, here is a very nice summary for us. Let me emphasize this part again. So how do we compute the volumes? We will first sketch the solid region and choose a typical cross section. Cross section means that this part. So we will try to find an expression for the cross section depending on X, and then the volume is given by the definite integral of A of X dx. So you need to determine the upper lower bounds for your integration. Limits of integration is important, and then you will integrate this to find the volume. Let's apply what we have learned in the previous example. Here you see what? You see a typical pyramid of one side of length 3, and the cross sections of this pyramid are perpendicular to the altitude x meters down from the vertex is a square x meters on a side. So if you take a cross section over the point x like this, then this side is of length x. It is given in this statement. Now I want to compute the volume of this pyramid. That's why first I need to start by expressing the cross-sectional area in terms of x, and it is a square, obviously, and the square of area of the square, this is the cross-section, which is a square, and area of square is given by x squared. That's why the volume can be expressed as, you are integrating the areas of cross-section from where to where. So look at your picture. You are summing up all those cross-sections from 0 to 3. This is the interval of integration. And now you can just compute it, because ax is given by the area of the square, which is x squared dx. So this integral is taken like that. And then you insert your points. 3 cubed over 3 minus 0 cubed over 3, right? So the result is 9 meter cubed. So this is the volume of this pyramid. Okay, let's look at the next example. This time we have such a solid object, and the cross sections here we have are rectangles like this. And there's an information in the statement that this angle is 35 degrees. And also the coordinates of this point is given as x minus this quantity. So this is your x coordinate. That's why this is the point x, as it is indicated here. What is the y component? Y component corresponds to here, the y-intercept. And this length is given by this square root expression. So this point here is minus square root of 9 minus x squared. Let me write it better. Okay, it is minus square root 9 minus x squared. And also at the symmetric part, this point will be again 9 minus x squared square root. That's why the length of the base of this rectangle, which is from here to here, is given by this quantity, right? Because half of it is here, half of it is here. Total length from this point on y-axis to this point is, of course, 2 times this much. Okay, now I can talk about the area of the cross-section, right? So let's shade the cross-sectional area. Okay, like this. And now I need to express this cross-sectional area. It is, in fact, the area of the rectangle in the figure. So what is the area of this rectangle? We know the base, we know the height. Height is given by x. So, okay, this is the height. Given by x, base times the height. Okay, then base is this much, 2 times square root 9 minus x squared, and times the height. Height is given by x. And then to compute the volume, what should I do? I need to integrate the areas of these cross sections over which interval? Let's see the interval. So x coordinate is here, and I need to sum up the areas of all those cross sections from 0 to 3. You see, this is the interval of integration. That's why I need to put here from 0 to 3. Okay, the rest is just completing things. From 0 to 3, this is what we have. 2x, 9 minus x squared, square root dx. How do you compute this integral? We need to use a substitution because this is not something that we know as a rule to integrate. So let's call this part as u then. U is minus like that. Du is, take the x derivative. And you understand then that where this part is u, the rest can be represented as du. You see, it is exactly this part. All you need to do is just take the minus to the left hand side. That's why this part is just minus du. So what you have for your integration in terms of your new variable is minus du square root of u. And then you can also transform the boundaries. You need to do that. If x is 0, the boundary for u is 9. And if x is 3, this is the upper bound for x, then the boundary for u, it becomes 0. So these are your new boundaries for your new variable u. It is from 9 to 0, I guess. Okay, let's compute the integral. This integral is computed as, this is a power function. You will add 1 to the power, you divide by the same power. There is this minus in front, and then you will insert your upper lower bounds to compute the result. Okay, so the result is, if you insert 0, nothing you have, and then you need to insert this value, minus, there is another minus here, plus 2 over 3, 9 over 3 over 3. Okay, the result is something like this. So I stop here for this video. Thank you for your attention.